Have you ever wondered what happened to the dinosaurs or why the moon looks like Swiss cheese? The simple answer is asteroids. Asteroids are rocky objects too small to be considered planets that orbit the sun in the asteroid belt. Meteoroids are even smaller rocky objects that orbit the sun, often made of a smaller piece of an asteroid or comet. A meteoroid that enters Earth's atmosphere and burns up before impact is a meteor, and if it does impact, then it is a meteorite. When a space object makes an impact, it leaves an indent called a crater, and these craters can be found on many planets and celestial bodies, including Earth, the Moon, and Mercury. In this video, we will take an in-depth look at asteroids and their counterparts, and all the types of damage they can do. Just to answer the ultimate question, should humans be worried about a fiery ball of space rock destroying our planet?
Asteroids were first identified or misidentified in the 18th century by Giovanni Paisi. Astronomers at the time thought there was a tiny missing planet between Jupiter and Mars, and were on the search for this new planet. Piazzi was the first to identify this planet, which was actually the first ever discovered asteroid, Circes. Hundreds of asteroids were identified in the following years, new discoveries exponentially rising in each technological development. Humans have come a long way when it comes to understanding and identifying asteroids, starting with naked eye observations to astronomical photography, and in today's age, orbiting space cameras that even analyze the composition of asteroids for us. Later, we will discuss how these technologies help us determine if an asteroid or meteorite is a threat to our planet.
Most asteroids formed along with the rest of the solar system and remain essentially unchanged in composition since formation. These unchanged bodies are known as primitive bodies. The supernova that set off the collapse of the solar nebula that formed our solar system threw gas and dust everywhere. Much of this debris condensed into planetesimals. These are pieces of rock, dust, and other cosmic materials. They can be as small as a few meters to hundreds of kilometers. Primal planetesimals were the beginning of the planets that we have in our solar system now. Some of these primal planetesimals collided together through gravitational forces to form these planets, but some of them remained as small and rocky leftovers, or asteroids. Three main classifications of asteroids, including C-type, S-type, and M-type asteroids. Astronomers analyze the spectrum of light emitted from an asteroid to measure its reflectivity through spectral studies. This gives them hints about the object's chemical composition. The most common class is C-type asteroids, known as dark asteroids. The C stands for carbonaceous, as these primitive bodies are full of the same dark organic carbon compound and silicate mixture as when they were formed. They are found in the outer part of the asteroid belt. S-type asteroids of stony or silicate composition are the second most common, also chemically primitive but missing carbon compounds. An increased presence of silicate materials and lack of dark carbon gives these asteroids higher reflectivity and clearer spectral lines than C-type asteroids. The difference in composition suggests that these S-type asteroids were formed in a different location from C-type. They can be found closer to the sun or on the inside of the asteroid belt. The rarest type of asteroids are M-type, made up of metals and identified using radar technology. Metallic substances reflect radar well and are difficult to identify with spectral studies. This third class of asteroids formed uniquely compared to the first two. It is theorized there was a large parent body with a molten interior, and when this interior separated, the heavier metal sank to the center. A collision caused this parent body to shatter, resulting in its metal core sending fragments flying. These fragments are what we know as M-type asteroids. Now that we have an understanding of what asteroids are, we are going to take a closer look at how they have shaped our solar system as we know it, including our neighboring planets.
In the formation of our planets, we shall take another look at planetesimals. Asterotation is a process of large enough planetesimals attracting smaller planetesimals via gravity and making them even bigger. Eventually, these forms become as big as Mercury or Mars, but these are not considered planets, but protoplanets. These protoplanets continue to grow and collect an assortment of other planetesimals. However, each impact created such heat that it melted the crashing planetesimals and the area it impacted. This creates something called planetary differentiation, with the heaviest metals, like the Earth's iron-rich core, and lighter layers forming on top. And that is the modern understanding of how planets are formed. The moon is a little different. For many centuries, the origin of the moon was mysterious. For as long as people could remember, at night, there was this giant cheese-looking object in the sky, looking down at them. It is only natural that the curiosity would take over and people would start to theorize. There were three original theories: fission, sister, and capture theory. Fission theory states, the Earth and Moon were connected to one another, but something happened early in its history that caused them to separate. Sister theory. The Earth and Moon were formed at the same time, but separately. This is believed to be how other moons were formed. Capture theory. The moon was once floating around in space until the moon captured it, like the moons of Mars, Phobos, and Deimos. The most accurate hypothesis for the moon is the giant impact hypothesis. A very long time ago, an object 1/10 of the Earth's size hit the Earth, causing a giant piece of an adolescent Earth to break off. This object is suspected to be the biggest impact Earth could withstand without shattering, which led to a splattering of rock vapor forming a ring around the Earth that slowly condensed and formed to what we now call the moon. Even if there is no definitive way to prove this theory, it offers the most amount of solutions caused by the previous theories. The moon's raw material comes from the Earth's mantle, and the idea comes from the previously stated rock vapor ring. And for those that ask why there is no volatile elements that would have been caused from the impact, the elements would have been lost in the high temperature phase right after the impact. The size formation of the moon to now, let's discuss why the moon and Mercury look the way they do. The moon is filled with many craters, and this is because in its early days the solar system was, to say the least, chaotic. We can still see the effects of this time on the surface of the moon. There are two different types of formations on it, Marias and Highlands. Marias are large impact craters that hit the surface with no force, that the hole from the impact filled with lava and then solidified. This creates a smooth-looking surface on the moon. The Marias are also used to discover 90% of asteroids. Estimation is made via the number of large craters on the moon's dark lunar Maria. The craters are preserved on the moon because of the atmosphere, and this allows us to guess how many impacts the moon and Earth have experienced over the past billion years. Next is the Highlands, which is older and is the part of the moon that is filled with a bunch of impacts and is mountainous. These impacts were probably made around 4.4 billion years ago at the oldest. With a similar look to the moon, let's talk about Mercury. The first close look at Mercury was made in 1974 by U.S. spacecraft Mariner 10. Even though the spacecraft was still over 9,000 kilometers away from the surface of Mercury, it still managed to get over 2,000 pictures of the surface. And in 2004, the spacecraft Messenger got even better pictures with multiple flybys of Earth, Venus, and Mercury. The spacecraft also measured the surface composition and mapped past volcanic activity. The surface of Mercury has many bright red craters like the moon, and even has some central peaks. Another feature on Mercury is scarps. Scarps are long and tall ridges that form from the shrinkage of the crust as the core cooled. Craters, however, are the main hallmark of Mercury. Mercury is filled with thousands of craters, and many are named in honor of artists, composers, writers, and other people who contributed to arts and humanities. Some names include Bach, Shakespeare, Van Gogh, and many more. Mercury also has large basins that could be over 1,000 kilometers in diameter. And now you may be asking yourself, since the moon and Mercury have big craters, could this happen to the Earth? Let's find out more.
Widely known impact in Earth's history is the event that caused the extinction of the dinosaurs 65 million years ago. According to geological evidence found by studying soil layers, there was a break in the fossil record only explainable by a mass extinction. Scientists found chemical changes in soil layers that matched the theory of a large impact causing this catastrophic event. They found elements that are commonly found in meteorites, such as iridium, in the soil layers that correspond to the appropriate time period. This evidence suggests that the asteroid was 6 miles across and caused a huge explosion on impact, leaving a 110-mile wide crater. Scientists even identified the crater associated with this event in 1990. Organisms that weren't directly affected by the explosion died shortly after due to the extreme environment and climate changes that the debris from the asteroid caused when it was thrown into the atmosphere. If it was possible 65 million years ago, is it that unlikely now? Since most asteroids follow orbits similarly to the planets and lie in between Mars and Jupiter, it is unlikely that one will hit Earth. However, sometimes they are thrown off their orbit either by each other or by Jupiter's intense gravity, and enter orbit between Earth and Mars. The reason Earth isn't as cratered as Mercury or the Moon is because of the atmosphere. Earth's atmosphere acts as a shield to space debris, and most meteors burn up before reaching the surface. Although very rare, sometimes meteors make it through this filter and do hit the surface, but are only large enough to cause property damage and not anything widely catastrophic. Most recently, in 2013, there was an instance of a small meteor hitting Earth in Russia. No one was injured from the direct explosion, which was as strong as a nuclear bomb, but the shockwave caused windows to shatter, injuring people in the nearby city. This sounds like a grim fate for our planet, but for anything to deal world-ending damage, it must be at least 1 kilometer in size, or over 3,280 feet. Asteroids and comets that enter Earth's orbit at the right place in the right time to be a little too close for comfort are known as near-Earth objects, or NEOs. Recognizing the risk of a large impact, NASA tracks NEOs that could potentially be of threat. In 1998, NASA began the Space Guard Survey with the goal to discover and track 90% of Earth-approaching asteroids greater than 1 kilometer in diameter. The survey has been very successful and reached its goal of 90% in 2012. Currently, there are no known NEAs on trajectory to impact Earth. Space is unpredictable and difficult to quantify in its entirety, but the science is there to dispel any fears of meeting the same fate as the dinosaurs. To further put anxieties to rest, there is an entire branch of NASA dedicated to planetary defense, the NASA Planetary Protection Office, that is actively working to improve technologies to deflect any trespassing space debris. There is a collision and deflection test taking place right now, launched in November 2021, known as DART, the Double Asteroid Redirection Test, aimed to hit the moon Dimorphos this year when its orbit is closest to Earth. The goal of DART is to test how effective this technology and methodology is. Quote, the objective is to measure the momentum transfer to the target asteroid by using telescopes on Earth to track the change in the orbital period of Dimorphos.
With so much information, let's summarize all that we've learned. To start, we discussed the history of asteroids, like how they were first identified and what they are exactly. We moved into how the terrestrial planets and moon formed, and next onto the craters of the moon and Mercury. And finally, we answered the big question, should we worry about something hitting the Earth? Which is a thankful no. No need to worry about mass extinction anytime soon. Well, that's it. Thank you so much for watching.